Hi, good morning. I'm Oliver Gao. I'm the director of Cornell System Engineering Program. I have been very fortunate to conduct what I call system conversations with our distinguished speakers that we bring to our Cornell Ezra System Seminar Series. Actually, today I'm really delighted and honored to have a conversation with Professor Cliff Whitcomb. Actually, Cliff is one of our own, but I'm very excited as I was talking to Cliff about giving it a more comprehensive treatment of system engineering and also system engineering competency. Actually, Cliff, he's a professor here with Cornell System Engineering Program. Actually, before that, he was a distinguished institute professor at the Naval Postgraduate in Monterey, California. And also before that, actually, he served as the chair. He was a former chair of the Department of System Engineering at Naval Postgraduate School. And of course, before that, actually, he had a very diversified and a successful career, from the naval and to other academic institutions, and also to many real-world practice. So I will stop here. I'll ask Cliff to, I believe he can give us more about, his career and also his work. So Cliff, I'm really excited. It's great to have this conversation with you. Please tell us more about yourself.
Right, thanks, Oliver. Thanks for having me here. I'm really happy to be here. As you mentioned, I was a distinguished professor in systems engineering at the Naval Postgraduate School in Monterey, California. So that was sort of a capping career event. But I started a long career in systems engineering and things related to systems engineering, which really started in my career in the U.S. Navy, where I started out as a naval submarine officer and served on board submarines, but then I transitioned to become a naval engineer. So I became a submarine designer, submarine naval architect, and worked on systems engineering programs and development of submarine systems to start with. And that was really my first exposure to looking at something more as a system and not in a particularly disciplinary focused perspective. So I had education as a nuclear engineer, progressed on to graduate degrees in electrical engineering, computer science, and naval architecture, and then a PhD in mechanical engineering. So I really ended up with a lot of disciplinary expertise in a lot of different areas. But by the time I got to my PhD, I was looking for something in systems that would relate more to a comprehensive context of a systems approach. And that's when I ended up at the University of Maryland working with Dr. Shapur Azarm and looking at multidisciplinary design and aspects. He had done some work on that for NASA, and I was very intrigued by that. And so being able to pull that into my own education and then apply that to the Navy was really my first look at systems engineering. And so by the mid-90s, the Navy itself was looking at standards for systems engineering. You look at various MIL standards and military standards that were part of the context of all military development. But in the mid-90s, a standard was set up, MIL Standard 499, which tried to standardize systems engineering. And that was one of the first attempts, I think, to really document and understand systems engineering from a perspective of application in Department of Defense. Now, Department of Defense have been doing systems engineering and developing it since the mid-50s, as well as the defense industrial complex. And so looking at systems was very important for success of Department of Defense and systems in their acquisition and operation of systems, simply because of the need for looking at more comprehensive aspects related to procurement of systems and operation of systems, with development of nuclear submarines in the 50s, looking at development of various warfighting aspects related to surface ships. First, Harry Jackson with his work in submarine design, transitioning submarines from traditional, more boat-like ships that then could be extended with nuclear power to unlimited submersions to stay underwater as long as they could, and so had to change the entire shape of the submarine now to match that environment. And then looking at Admiral Wayne Meyer, who looked at combat systems for surface ships and transformed the surface Navy. And both of those individuals took a very systems approach on things, and that really provided some basis, really, where I was working in general into development of systems engineering. And then as I progressed in my career, I ended up at MIT in this ocean engineering department, where I taught naval architecture and marine engineering, but also worked with the MIT System Design and Management program. So I was working there in that to sort of expand my ability in systems engineering beyond just military systems into many more different types of products and services and that sort of thing. And from there, went to University of New Orleans to teach naval architecture and marine engineering. But they also were interested in having me develop and teach courses in systems engineering, simply because there was a real desire in many of the industries that sent students to University of New Orleans to have systems engineering. And then they ended up at the Naval Postgraduate School, where I was recruited in 2005 as they were starting a systems engineering department. And I think that's where things really solidified in that aspect related to an academic department in systems engineering. There aren't a lot of them in the U.S. Currently, but we started one there. Ended up with hundreds of students in the program. Were able to support defense systems acquisition and education of defense systems engineers, both on active duty as well as defense civilian systems engineers, in a program that we found many sponsors that were very interested in educating students in these areas. We had our curriculum and our programs accredited by ABET. So we are accredited. There's very few master's programs that are accredited by ABET. 3 currently, Naval Postgraduate School, Air Force Institute of Technology, and Johns Hopkins University all have master's degrees accredited by ABET. And I think that this is something that shows that the education community and the accreditation community also recognizes systems engineering as an important field from an academic perspective that relates back to the practitioners of systems engineering and their education.
That's wonderful. Cliff, as you were kind of going through your career path, and I cannot help being impressed. Actually, you witnessed, right, all this during the past few decades, right, the evolution of system engineering. And of course, many of us know that system engineering has a very deep root from military, right? Ever since World War I and World War II. But nowadays, as your career evolved, you can see that system engineering was becoming more and more appreciated and used outside of the military field. Actually, yes. When you were talking about kind of system architecting, like a naval ship, or kind of how we can and they can help combat. I was thinking, nowadays, the whole world, we're facing, for example, climate change.
Yes.
We're facing food security and environmental pollution, and people usually said, we have to win this combat.
Yes.
And since you architected those submarines to win a combat, and I cannot help asking, how can we use this engineering framework, since it has been proved so powerful in probably the most fierce fight, which is in the war, right? We can win those things. And why can't we, or should we, use the system engineering approach to combat climate change? For many people, system engineering, they hear this a lot, but they don't know what exactly we mean by system engineering. Can you give people kind of some brief critical intro of system engineering, and why is our society today is in so much need of system engineering.
Yeah.
Yes.
At systems engineering, I think when the realization started to come in the 1950s of the fact that when you look at development and production of things, that looking at things with a disciplinary focus was not enough. It might have been before World War II. And one of my favorite quotes is from Rear Admiral Grace Hopper, who her quote is something like, before World War II, life was simple, and then we had systems. And since her background was she was one of the first people to work on the development of the computer, she is credited with having developed the first computer compiler. She is also credited with developing the computer language COBOL, and so she had a very initial view of computers and the fact that they could add something to systems that made them a little bit more challenging to deal with. And I think what her quote was related to was the fact that when you start to put computers in the context of physical systems and then had to work with humans in there, that what you were engineering now was something that could act more like a system, like an organism, that it could sense, it could respond, and it could do things without as much human intervention. And therefore, it started to take on aspect of, as I said, something like an inanimate organism that was even defined back in the 50s and recognized, to try to think of something as a more holistic view of something, because you look at any kind of a natural system as they did for inspiration, whether it's a human system or a solar system or something that they looked at, they started to say that you have to take into many more considerations than a single discipline at a time. It's not just mechanical engineering or electrical engineering. It's all of those in trying to balance something to get an overall system to operate as for some objective, and it took more than just that single discipline view. Another thing that started to change was that when you develop systems like aircraft and ships, I'll stick with the military things right now, that you typically had people who stayed with a company for decades and rose up through the ranks of engineering and eventually became lead engineer, and somebody who was a chief engineer who could actually oversee the development of all the pieces that it took to put an aircraft together, for example. But as companies diversified, the defense industrial complex started to become more complicated and complex itself. That sort of basis of companies changed and people started moving around, so you lost the ability technically to achieve the integration and success of the system as a system, and therefore you needed to have more of this individual and sort of engineering sense of people to work together to be able to create something that was a coherent whole system. And so in looking at systems engineering, it is engineering in that we are trying to develop things essentially that make things better for society, and we do man-made systems and approach it with engineering methods. The systems part is a little bit more challenging because it requires a lot of disciplinary expertise across different disciplines, or drawing on those parts of expertise into some much more of a holistic collaboration for development of a system. So we sort of lack something in the systems area where you could look at mechanical engineering, and of course you've got Newton's laws and mechanics of motion. You've got physics. You've got electrical engineering, and you've got Maxwell's equations, computational fluid dynamics, and Navier-Stokes. So you got a lot of basic science that underpins a lot of these things that were related to specific disciplines. Systems itself has only just started to define some of those aspects of a system science, but at least that approach and thinking of things as systems is what is overarching on systems engineering, to allow engineers that have some disciplinary expertise to be able to broaden their view and become sort of a T-shaped development where they have some depth in their knowledge of engineering and technical aspects, but also have some breadth to understand that there's more to it than just a discipline you may have learned. And so it's, in a way, in some ways it's breaking down barriers, but in other ways it's letting people know that there's development of this has to be a compromise among many different technical expertise. from this, computers and mechanical aspects and manufacturing aspects and operations aspects, and trying to understand what users and stakeholders need from a system. And I think that the military really spending and a lot of the taxpayer money on very large systems had to be very responsible for what they were doing, ended up in a situation where systems engineering became very important as a discipline. And I think that in this area, as you mentioned, in climate change or food security or energy or medicine and medical care, and you look at this, that these aspects related to engineering, which is really for society, and as socio-technical aspects have become much more important. And climate change has come to the fore as one with sustainability, and whether it's agriculture systems or energy systems or medicine systems, whatever, what have you, you can take these approaches and apply them into those areas, but it still has to be a holistic approach where you're taking people from an area that, as you're educated in a university, typically in a discipline, and you maybe have that lens, that focus on that, but you once you learn that and you realize that there's a larger perspective on how things exist in an environment and how the system is really very complex, and you can't have deterministic results on the expectations of what you know about something, and so you have to look at things from a much more broad perspective of things related to complexity, and not just a system, but things become systems of systems, and they exist in a broader sense of systems in relation to everything else. And in order to understand the implications and the ramifications of what you do in one area of a system, that you have to look at what are you impacting in another part of somebody else's system or another part of a natural system. So trying to take those basic competencies that start to be identified in the education of systems engineers and then broaden those to other systems developments, and the thinking of people that are developing systems that are not, say, military focused. Could use that same analogy that we started to develop competency models in the last 10 years or so that start to identify what are the skills that systems engineers need to have and exhibit in order to be successful. And so I think now we're looking at trying to say, how can we take those same skills and put those into other disciplines to see if we can actually add to that education component, if not at the undergraduate level, at the graduate level, where some people today think that systems engineering really is a graduate discipline at this point, because there's just not quite enough engineering core system science content to be able to educate undergraduates in systems engineering, although there are some schools that have found success in being able to do that. But many other perspectives, because this is evolving and growing, feel that at the graduate level is the right level to educate engineers and technical people in areas of systems engineering, so that they can have a more comprehensive view and application as a practitioner in the field.
Thank you, Cliff. When you were talking about this course, when you were referring to those military, examples or cases, actually, that made me feel optimistic about combating, all these current, societal systems challenges. Of course, I don't have any military background. All my military knowledge was, it can come from Top Gun.
Yeah.
But I was amazed about, you can see human beings, if we can produce those kind of design, naval ships and airplanes, they can travel in all those complicated situations and achieve a mission. So in that sense, that gives me the confidence that we can also hopefully win, the battle against, climate change and food security. But one thing, what I'm just thinking is, you can see now, as you mentioned, the complexity of the societal challenge, not only challenge, but problems, they're evolving so fast, such as that the need for system engineering or system science is humongous. While in the meantime, as you pointed out, actually, system science or system engineering as a discipline itself is still evolving, or more accurately, is trying to catch up, or trying to make ends meet, right, to suit all these societal needs. And I was thinking, okay, my analogy, okay, if we can build airplane, why cannot we, address the climate change? And as I was thinking along that way, I realized when you are architecting an airplane or a naval ship, right? It's essentially you're building a physical object, right?
Yes.
So, but when you are dealing with climate change, or even if you take enterprise as a system, also you mentioned systems. What I realized that first of all, human factors come in, and second of all, now that the cyber factors come in. It's really a human in the loop, cyber physical system. Actually, it's a human in the loop cyber physical societal system that when we think about climate change. So what do you see as the key challenge when we try to apply the systems and approach that has been proved very successful in military, in naval, in DoD, now moving it towards addressing these kind of systems challenge?
Yeah, well, yes, I think that in some ways part of this is because you see that in the military there's a very hierarchical structure and a very structure that's defined on, as you said, achieving a mission and developing that hardware in conjunction with the software and the people and the human factors around it. But it's very much dependent. The mission success is very dependent on the context and structure, and and there is a very hierarchical structure that says that we need to achieve these goals, and these goals are considered important enough that they go, at least in the U.S., right from the president down to Congress and to various parts of the military. So when you're working on this, it's a very cohesive system with definite results. You can see measurable results, and there may be some uncertainty in how effective a system will be in combat, but you still have ways of testing it and in a closed way of making decisions on it. I think and try to take that analogy into something like food security or climate or things that there are so many other variables in that mix that become people dealing with this in these social technical systems, that there are many stakeholders and they don't always have and can't necessarily be forced to have the same objective on this. And so trying to balance those objectives, but just getting people to understand that those objectives need to be balanced and should be balanced, and try to understand that there are methods that are documented as systems engineering methods to approach that. If you look at the systems engineering methodologies that are at least documented at the basic level in the INCOSE Systems Engineering Handbook, to name one reference from the International Council on Systems Engineering, you look at something like that they begin with in the first step of the process is business or mission analysis, and try to understand what it is, what are your objectives and your goals, as well as the next step is stakeholder needs and requirements development. So it is dealing with the stakeholders, and in this case we're talking about stakeholders that don't always have a common goal or objective. So you have many stakeholders, and so making decisions in those contexts and trying to keep a cohesive group of people like this in line to be able to get what's best. It's no longer quite as simple as what's best as if you win the war or win the battle. Mm-hmm. What's best could be different for different people, and so really trying to apply these methods in that context, as well as trying to balance the needs of people, becomes a very complex endeavor. As well as the fact you're dealing across international boundaries, you're dealing across boundaries of technology and limits of technology, and where technology can be applied and where it can't. And so you've got to look at this, as well as funding sources. It's not the same where you have a set funding source. There may be different funding sources and different resources that have to come together. And again, in the military, you have typically at some level somebody has control enough of the resources to be able to handle what's going on to meet some overall objective, and of course there's balances in there as well. But in the case of these socio-technical systems, it isn't quite as clear, and so you've got bodies of stakeholders who are trying to influence things and trying to look at it. And you, of course, don't have everybody on the same page of music, let's say, and trying to get to a certain goal. But those are some of the major challenges. I think technically we can approach many of these things and find some success. But even when you're trying to do that, the uncertainty related with this and what are we trying to achieve is difficult to understand because of some of the limits of our ability to model and simulate some of these things across these different areas to try to understand what might happen with something as we look at designing and deploying it, that there's a lot of emergence that can happen that's hard to predict up front, and therefore you have to be willing to also deal with the fact that you may have to be constantly looking at aspects you're putting out there, get some kind of decision and go forward, but then the environment changes, whether it's the resource change or there's a different impact or something, or some other event happens to change this, that you have to be able to be adaptable, not just in your system, but also in your stakeholders to understand that you may have to continue this kind of decision making in order to try to determine what the best objective is and how we're going to meet that in a more continuing basis. So it becomes a real challenge in the dedication and the amount of time it takes to get people working towards a common goal when that goal can be different for different people.
Please, thank you so much. Actually, I think, I really appreciate, when you answer my question, actually, you hit the very fundamental key point very sharply, and then you pointed out. It's something, and I agree with you. It's really, when we apply the systems approach in designing a neighborship to addressing, like climate change challenge, and you pointed out the major barrier, the major difficulty is really the lacking of a structure. Because I believe so. Because if you think about this, actually, by the way, that kind of makes me less optimistic. Maybe than 5 or 10 minutes ago when I thought about if we can build an airplane, we can address climate change.
Yeah.
Now actually they're not the same. And you're right. It's really the hierarchical structure. It's not necessarily hierarchical, but it's really the rigor of that structure ensures the execution, right, of the mission and to achieve the goal, right? That is something. And speaking of that, I think kind of for the whole society, for the whole world, assuming that we now agree that a climate change or sustainability is a key challenge. As you mentioned, even having people to agree upon these common goals, there is already difficulty there.
Yes.
And that difficulty is not due to the lacking of structure. It's due to the lacking of course, kind of different culture, different history, right? And also different culture at different positions, different stages.
Yeah.
And even after we come upon an aligned common goal, and when we come to the point of execution, and that lacking of that structure, right, immediately become another barrier. So when I look at both these key challenges, I feel that lead me to, because whether to get the people come upon this common goal, or building or establish a structure to support the cause, I think that all depend on, I feel, evolution of people, of human beings. So that can lead us to, I think, kind of, yes, given the goals, given those challenges, and given where people are, and it seems like, and we agree that a systems approach is really going to be critical for us to address those challenges, because there is no way you can just rely upon a civil engineer or a mechanical engineer or an economist to address those things. So how can we get our current level of humans, our education, our training, from a current level to a level that where our people will be ready to address that kind of? So I know that you've been leading this INCOSI effort, to do a survey. I believe more than 6,000 system
Right.
engineers and more than
Yes.
1,200 managers
Yes.
across all multiple institutions or agencies to find out um, not necessarily how, but at least what we need to equip our people to be able to address it. So please, I think I would like to spend the rest of our time to dive into that because I now with our previous discussion, now I realized why you study this, why you study this competency, for system engineers.
Yeah.
So tell us more about that study. Why you did that study, how you conducted that study, and what you found out.
Yeah. Well, you're right. You're right. The areas of competency, which means what people have as their knowledge, skills, abilities, and behaviors to do a job. Where competencies reside with the job that you're trying to get done, because you define the job and what has to be accomplished in that job by the competencies required for it, and then people develop competence to be able to be matched to a job, and that they have knowledge, skills, and abilities. And where do they get that? Well, they get that from education and training. They get it from on the job. They get it from their development of their personality, all these different things. They develop competence. The idea is to try to match them to a particular job or job position that requires certain competencies. So the idea of modeling competencies and documenting them has been around for decades. But one of the areas I think became fascinating to me in, say, 15 years ago or so was that although at least the U.S. government, and I'll go beyond Department of Defense, U.S. government, identifies dozens of different kinds of engineers, and they can identify the competencies for those engineers. I mean, electrical engineers, typical things you would think mechanical, but also fire protection engineers, nuclear engineers, many different competency models, but never one for systems engineering. And this is in both parts of government agencies, both the Office of Personnel Management and the Office of Management and Budget and Bureau of Labor Statistics keeps track of careers and jobs on an annual basis. There just was no definition of systems engineer, and yet in the Department of Defense, in that systems sort of career field they have, there's probably about 40,000 people that are working in that field. And if you look at all of defense acquisition, that's probably 150,000 or more people that are working in that field doing defense systems acquisition in some form or another. So there's quite a number of people that need to be educated, and yet for all these different fields of application and practitioners, there just was nothing in systems engineering. So in around the sort of, I guess, 2009, 2008, 2009 timeframe, I started working in a working group with the National Defense Industries Association, their education and training working group, to look at, we were trying to organize these different companies that were members of this organization to say, what do you do for systems engineering? How do you identify the different competencies? And we tried to get companies to give us their competency models so we could start to look at harmonizing what kind of competencies could we define for systems engineering. And we found that as we collected them from places like NASA and MITRE, and we had Department of Defense had a competency model for their systems acquisition that wasn't necessarily officially recognized by the U.S. government-wide, but Defense had one. Mm-hmm. And many other organizations contributed competency models, and it was the first look we had at trying to organize something coherent out of all of this competencies. Well, at the same time, in around 2010, the INCOSE UK chapter developed a system engineering competency framework they had published. And I think in the UK is a little different because in their way of sort of certifying or chartering engineers, that they needed this basis of competency to try to understand what systems engineers do there. So they actually published a competency framework in 2010 that was put out, and we also took that in. Well, this NDIA effort led to some efforts within Department of Defense to try to get a little bit more comprehensive look at competencies. And at the time, in the Secretary of the Navy's office, there was a Deputy Assistant Secretary of the Navy, Mary Lacey, who was just really interested. She was the chief engineer of the Navy, essentially. She was in charge of all the research and engineering enterprise for the Navy. Just wanted to know, okay, what do my system engineers do? And so let's find out by doing this. So I was selected to be the principal investigator to look at surveying systems engineers in the Department of Defense. We did the Navy, Marine Corps, Air Force, Army, Missile Defense Agency. And as you mentioned, we surveyed, or it took about several years to actually get the survey together, structure panels of people who are practitioners in the field, their supervisors, and trying to understand, collecting information. We worked with the Office of Personnel Management to gather this together and understand what is out there and documented for jobs where people do systems engineering for Department of Defense, and then start to pull those into the context of definition of the knowledge, skills, and abilities, then structure them into sets of competencies, and try to find out which competencies were critical for people to be able to perform their jobs as systems engineers. The important thing here out of this that resulted from this was a system engineering competency model for Department of Defense, primarily for Navy because they funded it, but they also, through working with collaboration with Office of Secretary of Defense, managed to get this competency model useful for all these other agencies. But for the first time, now with a model that was validated in accordance with the regulations that the government had in place, that you could not require people to do systems engineering tasks because it hadn't been studied yet. And so now that this competency model has been created in accordance with the Uniform Guidelines on Employee Selection Procedures, it can now be used for all high-stakes functions of performance appraisals, job, and you can require people in systems engineering for the Department of Defense to have those skills. You can interview them on it. You can, if they don't have the skills, you don't have to hire them. You don't have to promote them. And so it was the first time we were able to get to that level on par with the competency models that existed. So this model has now been developed and taken by the Navy and put into their competency network, so it becomes the basis that anyone, at least in the Navy right now, can require their systems engineers throughout their workforce to have systems engineering competency skills. It also provides a large context for people to identify the kinds of skills they need for systems engineers, and it became very specifically defined, so that if you wanted to a hiring manager wanted to hire a system engineer, they could actually now look at a comprehensive model and say, oh yes, these are the skills that I want, instead of having to try to imagine the skills that they might need or from their own experience. This is something that was put together by a large group of practicing systems engineers as well as their supervisors and their supervisory context in these larger organizations which helped oversee this, so they could with confidence know that these were the skills that I should be looking for to hire, and that I can now require my employees to actually be able to have some competence in, and define through levels of entry level all the way through expert to know how you should progress in your career, to develop and have these competencies to progress. Now, because I was at the same time a member of NCOSI was also working through their competency working group in conjunction with the NCOSI UK, and I was a member at the time of the competency working group, and we pulled this information from NDIA and the information from this Navy model and the NCOSI UK model, and we restructured the NCOSI System Engineering Competency Framework based on the UK framework, and in 2018 published the first System Engineering Competency Framework. This one was an internationally developed and, I would say, sanctioned, but at least the systems engineers on this council from the System Engineering NCOSI Council and the working group, and then had this approved. We thought as an international collaboration we had a set of competencies and knowledge, skills, abilities, and behaviors that define what a system engineer should do. So this is now available internationally for people to understand. Whether you're in engineering or not, you could start to use these. So this became something that's available in 2018. Now, since then, since I took over as chair of the System Engineering Competency Working Group, we also updated the model, and we also developed a System Engineering Competency Assessment Guide, which provides a little bit more structure on then how do you assess whether people have these competencies. And as you mentioned, this book will be published. Wiley's going to be publishing this. I'm one of the 3 main co-editors with Ian Preslin from the UK and Laurie Zipes from here in the US and myself, and edited this with a large working group and contingent of people from various industries, international, globally recognized systems engineers. We put this together, and that will be published in, as you said, in January, and that will document and be available to anyone to be able to use as a basis for understanding some of the competencies required for systems. And we tried to be not so specific on systems engineering that could only apply to engineering. There's competencies related to, in general, systems engineering, modeling and simulation, aspects related to management of systems, and other areas that cross-cut the development of systems. We tried to make it as general as we could without taking so long to develop this that we never would have finished. So we expect that now that this will be published, it will be available to a much wider community rather than just a model that was developed by a professional society, offered out to people in the world, but we don't quite have the marketing and the aspect to get that competency framework out there. But I think this will make this model much more internationally available through a major publisher like this, where now anyone who's working in a systems area can start looking at this competency model and looking at aspects of it and say, how can we work aspects of relationship sensitivity of systems to what we're doing? Because the elemental parts, the statements that are within the competency model, are actually structured as learning objectives in essence, and they're defined using Bloom's taxonomy, which is widely used as a basis of learning and education and training, and therefore they can easily pull that into what do people need to know, what kind of skills do they need to have, what levels of proficiency do they need to have it at. And they can start from there, and then they can tailor that with their own specific competency. They can either change the adjectives in it or change it to their own field, or they can actually add things to it if they think there are things missing. So what we're hoping for is to start this in a broader international context of what it takes to define what systems engineers need to know and what they need to be able to do to accomplish systems engineering, but also translate that into the development of any kind of system, an assessment of any kind of system, and collaboration in developing any kind of system, or to get some kind of objective out as in a system result that you might be looking for. So I think that the ability to communicate this more widely across a more sort of general audience is one of our goals for this Systems Engineering Competency Framework and Assessment Guide. And because we included an assessment guide, it makes it a little bit easier for people to say, well, I see this competency and I see this knowledge or this skill statement. What can I do to assess somebody? Because not everybody's in the education business, in academia or any kind of education where they kind of know how to teach something and then assess whether somebody knows it, or they can look at somebody who needs a skill in a particular area where they're used to assessing people. In general, of course, things like commercial aviations, you have to assess pilots and certify them. In the medical profession, you have to certify doctors and nurses so that you know that they can effectively practice their trade. But this hopefully will provide some basis for having a lot of different people understand how to take a systems sensitivity and a systems approach into anything that they're doing. But because it's been defined and well-defined as a source and somewhat of a standard, then it can become a resource for systems. Now, as a part of another context there, that the global awareness of developing competencies for all kinds of careers and fields has also been blossoming everywhere for at least the last decade or more. So there are many different competency models out there now. There are hundreds of them in different fields and areas, all the way from restaurant workers to construction workers to accountants. I mean, you just name any field, there are now competency models, and they're starting to be put out in forms that they can be searched and found using computer algorithms. And so now you can start to search for things and pull things together and then tailor structured competency models to work on this. And in that light, a group of people at IEEE, the Institute for Electrical and Electronics Engineers, started an effort about a year ago to develop a standard for defining competencies. And this standard was just approved this week to be published, and so that when that comes out, that will now form the basis of an international standard in how to define competencies and competency models and competency frameworks to try to allow some way to maybe harmonize all these different competency models into a more coherent structure. Plus, it talks about how you use competency models. So IEEE recognized that this is something that there are competency models everywhere, but not everybody knows they exist. Not everybody knows how to use them to the best effect. As they've also developed as a complementary standard to that is one that says how to put them competencies into an appropriate digital format so that they can be found. Mm-hmm. And so that's another standard that talks in great detail on the data structures and how to organize those so that they can be discovered. And that way, if you can discover them digitally and you can bring them in, you can start to form your own competency models from all these disparate sources by doing data searches and data analysis and put them together, discover them, pull them together, work with them, and develop competency models that have different dimensions in there. So if there becomes a sensitivity that all these issues are more system-like, a systems engineering competency framework that's out there in conjunction with other frameworks on people that work in agriculture or energy or medicine or wherever it is, they can pull their pieces of their models together, and if they can put them in an appropriate digital format by some sort of standard, then we can start to pull these together and start to have all kinds of organizations and enterprises identify systems competencies as needed in their context to be able to provide more of an educational basis that could spread through enterprises, companies, educational organizations, and down to educating people to have a sensitivity to this. If we're going to tackle these kind of very broad system challenges, we're going to need to start educating more people on this and having organizations that hire people that have these kind of skills so that they can be recognized for their ability to do this and meet some objectives they have in a system sense, because they know now that they have people that have the skills can do this. And I know it's more of a long-term, on the horizon effort, but the more we can pull that into place, I think the sooner we'll be able to have organizations and enterprise have some basis for finding success in applying a systems approach in many different areas other than just systems engineering.
So, Cliff, thank you. I think this is so important. Given our discussion about the key barriers, in applying system engineering to addressing those key challenges, and we all agree, we both of us agree that in the end, it's really, the training of the human capital, right? And of course, the training of human capital. And the thing is really, how do you even evaluate this competency, and then how do you achieve the training purpose of building competency among all those people? Congratulations on that book, and I believe you can see the book will be so important. And as you pointed out, it's not only going to be just because system engineering in the end, I feel it really kind of cut across all the different fields beyond the traditional engineering field. Right, it goes across to agriculture, right, economics, the social technical system. So I can see the potential impact of that book. Yeah, right. It's really important. So of course now you can see that we are, with all that insight and the knowledge, behind writing the book. So now, as a faculty, on our program, and then, what do you think? Of course, I think Cornell System Engineering program. We are relatively small, but somehow I feel we enjoy a very good, position or reputation for the program to build something that can match up to what you had, as a vision in that competency. So, because I heard from David Schneider, our colleagues. Several years ago, when there was a retreat among the MN directors and with some industry partners, and they came to a conclusion that they said, actually, system engineer should be, every engineer should be trained with system engineering approach and analytics. So with that, of course, now you can see that we have this graduate level program to train our people to be system-oriented, systems engineer equipped, and also system engineer competitive,
Yeah.
competent, right? So in that sense, what do you think are the key pillars or areas we should focus our limited, resources on, so that we can really become a spearhead, because we're small, which is not bad because we can be agile, and also we can, for example, imagine that if your book comes out in January, we can adjust our program to equal to your book, say by the fall. So what do you think as the key areas? Of course, not only just Cornell system engineering program, but all the system engineering training education programs. From your point of view as an author, as a visionary thinker for system engineering competency, what would you like to happen?
I think that one of the things in particular, and I'm going to start here with Cornell, is I see that in the systems engineering program here, in the Master of Engineering and various Master of Science and PhD programs, the ability, at least at Cornell right now, to look at where Cornell has identified aspects related to sustainability and climate change, and the sheer number of different sensitivities there are here to different approaches, and the infrastructure here to look at food security and energy and health and all these different areas that exist in the existing coursework across campus and in different areas, can provide that ability to very, as you said, agile, very quickly adapt to structuring some of this into a systems engineering program context, but also relate back to what kinds of learning objectives and aspects related to those programs could they have that relate themselves to systems thinking and systems approaches, even beyond what they are probably already doing, but looking at it as a sense of collaboration. At least here within the university at Cornell, I just see that there's tremendous potential for looking at trying to leverage these different opportunities into an approach that not only hits systems engineering, but also different sensitivity to systems in other areas that are related to development of all kinds of systems and approaching that. I think looking at it across in a larger context, I think that in order for other universities and other educational institutions to be able to address some of these more global, worldwide issues like this, they really do have to have some way to collaborate with other programs that have the expertise in these areas, because you have to have expertise. You can't just do systems engineering and approach a challenge like food security and agriculture unless you have people that understand that, as well as climate and energy and all these other things. That you have to have experts in these areas who can actually provide the necessary technical competence in that domain.
Yes.
In order to have people have a sensitivity to that. And it's not that a system engineer has to try to understand all these different things. A system engineer has to understand at least some technical depth to understand what can be done and what can't be done based on modeling, simulation, mathematics, and physics, and science, biology, chemistry, all these different things. But then be able to understand how they can apply these different systems approaches in these different areas and collaborate across these different areas. So I can see the structures of cross-campus collaborations, multiple university collaborations, development of things, centers and institutes that focus on this and provide collections of resources and expertise and guidance on how to approach these different problems, and try to structure things so that they can either start to look at sort of generally addressing aspects related to something like sustainability, which can go across different things, or picking different areas where they want to focus on sort of, whether it's food security and agricultural systems, or somebody else may want to focus on climate issues, somebody else on medical and whatever the health and things like that. So I think you can either try to have parts of all those in a single organization and focused in some way, or I can see other parts of it, focusing on specific issues in collaboration. But it's going to be hard for universities that don't already have, organizations, institutes that don't already have a lot of this deep expertise in these areas to really be able to pull together without collaborating across sort of institutional boundaries.
I see. Yeah. Thank you, Cliff. I feel, every time you ask a question, you always hit, the so fundamental key thing. I feel kind of the key point I got from you is really, yes, system engineering can be very powerful. System engineering can be very general. But the real advantage will come from pursuing synergy, right? Kind of having system engineering to be really closely, seamlessly married with, the specific domain area. So that way, both sides, the power will be liberated. Right. Yes. So I really like that approach, and actually we do have the vehicle here. And I think in the system engineering program, of course, soon we are going to, we're building towards the system institute. Yeah. I feel that can be really a vehicle to really implement the vision that you had. Mm-hmm. Kind of, it's like the way we work on energy system. It's really, I think, kind of combining some fundamental the system engineering courses from curriculum point of view. Right. If you think about, we really want to train. Either it's an agriculture scientist or a climate scientist, but they're interested in system engineering. And then when they come to the program, they're exposed to all these system engineering approaches, but also bringing with them their domain scientific knowledge and empowered by this system engineering approach. And then they will apply those things back in their domain to address those challenges that you and I just discussed. I think this is beautiful. So I know that our time, and it's coming up. So just the final couple minutes, and I do know, and I appreciate so for your new book or anything you want, if anything you want to talk about, and I do agree with you that I think we should try our best to get the word out about this book, because I feel this book is really going to have tremendous impact. So I will leave all the rest time to you. Yeah, please go ahead.
Okay, well, thanks, Oliver. I think the part of what I think I'm most excited about is this looking at trying to see what we can do to facilitate and lead aspects related to getting these kinds of systems-related learning objectives out into broader communities, because the more you can look at this in different ways of having systems approaches be put into different curricula and as a basis for learning, whether it's education or training, that at least raising awareness and then raising knowledge levels and skill levels in dealing with these. I think if you can get people to understand what it is that could be done and then provide them the basis for how they can understand what they need to know and what they need to be able to do, and then be able to have that be something that when they get to the workplace or when they're in the workplace, that they actually find that there's this synergy, as you mentioned, that can actually be helpful in companies achieving their objectives, about enterprises doing the same thing. I think that, as I said, one of the things that really interested me in this when I started this more than 10 years ago was the fact that here I'm teaching systems engineering, and I'm always wondering, am I giving the students what they need to know, and I wanted to know from my own experience. I knew what I thought was important for systems, and in talking to sponsors of students and looking at different sort of interactions with places like Nkosi, trying to understand what are some of the bases for systems engineering, but I really couldn't find that real sort of more, at least somewhat definitive source of what are the learning objectives and competencies that are required to be a system engineer. I knew that as a naval architect, if I wanted to know what some of the fundamental things to do as a naval architect, I could turn to the 3-volume Principles of Naval Architecture. I could look up all kinds of things, at least as a starting point, or I could go to various colleagues that were working in the field of naval architecture. Same thing with electrical engineering and power systems. But when it came to systems engineering, I could always talk to colleagues, but there wasn't something that I could go to that was the principles of systems or principles of systems engineering that had this, that I felt comfortable I could refer to that and say, okay, well, I know that as long as I'm teaching these principles and going out there. And so there's been some efforts lately to try to understand the principles of systems engineering. And so these been some publications out there from systems engineering experts in COSI to try to define those principles and then promulgate those and get them out there so that people can start to understand now, even beyond the development of competency, what are some of those fundamental principles that you can draw on to understand systems. And I think that'll go even further into trying to convince people that there's something there, that if you can identify the principles that are the basis of what you're doing, I think people that are more trained and educated and in that way will at least can see what some of the fundamental principles are. So I'm also very excited to look at how we can once identify them, and then we can start changing them from there or redefining them or turning them into more of a basis for what underpins systems science and systems thinking, which I think is a piece that we still need to really work on to try to define this. Because the competencies identify what practitioners do. Mm-hmm. We'd like to know really what could they do better in the future and what kinds of things are we missing. And I think if we can understand some of those fundamental principles, we can start turning those into things that also develop aspects related to education and training that we can start integrating into these competency models and competency frameworks going forward, and really turn it into something that has even more relevance to the different fundamental principles that are necessary to actually accomplish a successful systems approach, no matter where you apply it.
Yes, absolutely. And actually, I think, thank you for thinking that way. It's not only you. I think every educator, teacher, or professor teaching system engineering, and I think kind of we have the same problem. Okay, what should we teach the student? Yeah. And then we try to find some principles. You cannot find it, right? And now I think your book is coming in. Hopefully, that will help fill that void. Of course, I think for any audience, watching this, if you want to know more about what exactly system competency or the framework should be, or it's going to be like, actually, Professor Whitcomb, he will be delivering Cornell System Ezra roundtable seminar in about 15 minutes, and also that is going to be recorded and put online. It's recorded and streamed in real time, and also recorded, and it will be put on YouTube momentarily. So if you're interested in learning more about the details, so there is going to be a follow-up. So please feel free to if you're able to please join the seminar series. So Cliff, thank you so much. It was really a great pleasure.
Yeah, it's great. My pleasure too. Thank you all.